Look up at the night sky. What do you see? A scatter of stars, maybe a planet or two, the serene glow of the Milky Way. But hidden in that infinite blackness are some of the most violent and mysterious events the universe has to offer: gamma-ray bursts. These are not just any cosmic explosions. They are the universe's most powerful detonations, packing more energy in a few seconds than our sun will emit in its entire 10 billion-year lifetime. Imagine fireworks, but on a scale so immense, so ferocious, they can outshine entire galaxies. And here's the wildest part: we're seeing them from billions of light years away, meaning they happened when the universe was just a fraction of its current age. These bursts are like cosmic messages in a bottle, traveling across unfathomable distances to reach us. Some of them come from so far away, their light has been journeying since before Earth even existed. That's right, when you witness one of these distant flashes, you're peering back in time to the earliest chapters of the cosmos. But what causes them? How do they manage to be so staggeringly bright? And what secrets do they hold about the universe's most extreme environments? Today, we're diving into 30 mind-blowing facts about the most distant gamma-ray bursts ever discovered, each one unlocking a piece of the universe's grand puzzle. From colliding stars to the birth cries of black holes, these bursts are more than just celestial spectacles. They're clues about how galaxies form, how matter behaves under the most extreme conditions, and even how life itself might owe its existence to these cataclysmic events. So buckle up, we're about to take a journey to the edge of the known universe, where time bends, energy defies imagination, and the cosmos puts on the greatest light show of all. And trust me, by the end, you'll never look at the night sky the same way again. Gamma-ray bursts are the ultimate cosmic powerhouses, capable of unleashing more energy in a single second than our sun will produce over its entire 10 billion-year lifespan. Picture this: a flash so intense it briefly outshines every star in its host galaxy combined. That's the staggering reality of these eruptions. When one of these explosions goes off, it can be visible from halfway across the observable universe, even if it lasts just a few milliseconds. What makes them so blindingly bright? The answer lies in their extreme physics. Unlike supernova, which release energy in all directions, gamma-ray bursts channel their fury into narrow, ultra-focused jets. This concentrated beam amplifies their luminosity to mind-boggling levels, like tightening a flashlight beam into a laser. But here's the real kicker: their brilliance isn't just a spectacle. It's our cosmic lifeline to studying them. Because they're so ludicrously energetic, we can detect them from distances so vast. Their light left its source when the universe was just a toddler. Some of the most distant bursts we've observed erupted when the cosmos was only a few 100 million years old. That's like capturing the echoes of the universe's first fireworks. Without their sheer brightness, these ancient signals would have faded into oblivion long before reaching us. And that luminosity holds secrets. By analyzing how their light dims and shifts across wavelengths, astronomers can piece together how matter behaved in the early universe. It's like finding a fossil, but instead of bones, we're studying the afterglow of a cataclysm that briefly outshone existence itself. These flashes are more than just records, they're active probes, illuminating the cosmic dark ages and revealing how the first stars and galaxies took shape. So every time we spot one of these distant bursts, we're not just witnessing an explosion, we're decoding a message from the dawn of time. The universe doesn't just produce gamma-ray bursts, it crafts them in two distinct flavors, each with its own explosive origin story. On one side, you have the short bursts, blink and you'll miss it eruptions lasting mere milliseconds to a few seconds. These are the cosmic equivalent of a sniper's bullet, precise, sudden, and often tied to the violent mergers of neutron stars, those ultra-dense stellar corpses. When two of these stars spiral into each other, their collision sends shockwaves through space-time, unleashing a fleeting but unimaginably powerful burst of gamma rays. Then there are the long bursts, the marathon runners of the gamma-ray world, stretching from a few seconds to several minutes. These aren't just longer, they're fundamentally different beasts. Picture a massive star, tens of times heavier than our Sun, reaching the end of its life. As its core collapses into a black hole, the dying star doesn't go quietly. It screams across the cosmos in a supernova so colossal, it funnels its energy into twin jets piercing through space at nearly light speed. That's a long gamma-ray burst, the death cry of a star, amplified into a beacon visible across the universe. Here's where it gets even more fascinating. The most distant gamma-ray bursts we've detected, the ones whispering to us from the universe's infancy, are almost exclusively long bursts. Why? Because the early cosmos was a star-making factory, brimming with massive, short-lived stars destined to explode as supernova. Those cataclysms left behind the long bursts we now spot billions of years later. Short bursts, meanwhile, require neutron star mergers, which take much longer to occur, time the ancient universe simply hadn't had yet. This divide isn't just academic. It's a clue to how the cosmos evolved. Long bursts act as cosmic archaeology, revealing where and when the first stars lived and died. Short bursts, on the other hand, are like forensic evidence, showing us the aftermath of stellar collisions in more mature galaxies. Together, they paint a fuller picture of the universe's life cycle, from its fiery beginnings to the intricate dances of dead stars today. So next time you hear about a gamma-ray burst, listen closely. Its duration tells a story billions of years in the making. Gamma-ray bursts do something even more extraordinary than just lighting up the cosmos. They bend time itself. Or at least they let us do it. When we detect a burst from 12 billion light-years away, we're not just seeing an explosion in distant space. We're witnessing an event that occurred 12 billion years ago, back when the universe was less than a tenth of its current age. That light has been traveling across the void since before Earth formed, before the Milky Way took shape, even before most of the stars we see today were born. These bursts are like cosmic time capsules, carrying pristine snapshots of the universe's youth straight to our telescopes. But how does this time travel trick work? Think of the universe as a vast, expanding fabric. As light from a gamma-ray burst journeys across this stretching cosmos, its wavelengths get pulled along with the expansion, shifting toward the red end of the spectrum. This redshift becomes a measuring tape. The more extreme the shift, the longer the light has traveled, and the further back in time we're looking. Some of the most distant bursts ever recorded have redshift so high, they place their origins within the first few 100 million years after the Big Bang. That era, often called the Cosmic Dawn, was when the first stars flickered to life in a universe still thick with primordial gas. And here's where gamma-ray bursts outshine even the most powerful telescopes. Normally, spotting individual stars or galaxies from that far back is nearly impossible. Their light is too faint, too stretched by time. But a gamma-ray burst, it punches through the obscurity like a flare in the dark, its brilliance undimmed by the eons. When one erupts, it briefly becomes the brightest thing in its galaxy, shining a light on everything in its path. Astronomers use that flash to study the gas and dust it passes through, analyzing absorption lines in its afterglow like forensic clues. These chemical fingerprints reveal what the early universe was made of, how quickly it was evolving, even how transparent space was before the first galaxies fully lit up the darkness. What's truly astonishing is that without these bursts, entire chapters of cosmic history would be lost to us. The period before galaxies fully formed is notoriously hard to observe. It's often called the universe's dark ages. But gamma-ray bursts cut through that fog. Their light acts like a backlit probe, illuminating the structure of the early cosmos in ways nothing else can. By catching these ancient flashes, we're not just glimpsing the past, we're decoding the conditions that shaped everything that came after. Every distant burst is a messenger, carrying secrets from a time when the universe was still taking its first fiery steps. In the vast cosmic timeline, some gamma-ray bursts stand out not just for their power, but for how far they've traveled to reach us. The current champion of distance, GRB 090423, holds a staggering title. Detected in 2009, this burst's light began its journey when the universe was a mere 630 million years old. To put that in perspective, that's just 5% of the cosmos' current age, a time when the first galaxies were still clumping together from the primordial darkness. What makes this burst so special isn't just its age. It's what it reveals about the universe during its infancy. When astronomers analyzed its redshift, they realized they were looking back to an era called the reionization epoch, a cosmic turning point when the first stars and galaxies began burning away the thick hydrogen fog that filled space. GRB 090423's afterglow acted like a lighthouse beam piercing through that ancient haze, giving scientists their first direct glimpse into conditions so early in cosmic history. Without this burst, much of what we know about that formative period would remain theoretical. But here's the twist: this record holder almost went unnoticed. The burst itself lasted just 10 seconds, a fleeting blip in the data. It was the afterglow lingering at infrared wavelengths that betrayed its true significance. As telescopes scrambled to observe it, the light's extreme redshift confirmed its origin in a universe still in diapers. That afterglow became a treasure trove, revealing signatures of heavy elements like magnesium and silicon, proof that even at this early stage, stars were already seeding the cosmos with the building blocks of planets and life. The discovery reshaped our understanding of how quickly the universe got to work. Finding such a distant burst meant massive stars were living, dying, and exploding far earlier than many models predicted. It hinted that the first stars weren't just tiny pioneers but towering giants, burning bright and fast, their deaths lighting the way for everything that followed. So while GRB 090423 may no longer hold its record forever, astronomers are always searching deeper. Its legacy endures. It taught us that the young universe was far more dynamic and violent than we imagined, and that gamma-ray bursts, when caught in the act, can illuminate even the darkest corners of time. Gamma-ray bursts aren't just cosmic explosions, they're the universe's ultimate survey tools, shining flashlights into the darkest corners of space. Imagine trying to map a vast, foggy forest with only a handful of scattered lanterns. That's essentially what astronomers face when charting the cosmos, but GRBs change everything. Their fleeting brilliance cuts through intergalactic haze, illuminating the invisible scaffolding of the universe, the so-called cosmic web of gas and dark matter that connects galaxies like threads in a spider's silk. Here's how it works. When a gamma-ray burst's light races toward us, it doesn't travel through empty space. It passes through clouds of gas, filaments of dark matter, and the remnants of long-dead stars. Each interaction leaves a fingerprint on the burst's afterglow, like a stain on a white canvas. By analyzing these spectral imprints, scientists can reconstruct the composition and density of matter along that precise line of sight. It's cosmic tomography, using bursts as backlights to X-ray the universe's hidden anatomy. Some of the most startling revelations come from bursts dating back to the reionization era, that pivotal period when the first stars ignited and their ultraviolet radiation began tearing apart the primordial hydrogen fog. GRB light from this epoch carries telltale signs of being partially absorbed by that leftover gas, like sunlight filtering through morning mist. The degree of absorption reveals how quickly and unevenly the universe transformed from opaque to transparent. One particularly ancient burst showed patches where the fog was already clearing just 700 million years after the Big Bang, suggesting the first stars formed in intense, clustered bursts rather than a steady cosmic sunrise. What makes GRBs indispensable is their impartiality. Unlike quasars, another common light source for mapping gamma-ray bursts occur in all types of galaxies, including small, unremarkable ones that quasars rarely inhabit. This gives astronomers a democratized view of matter distribution. free from the bias of only studying unusually bright or active galaxies. A recent survey using 67 GRBs revealed surprising voids in the cosmic web regions where matter is sparser than predicted, challenging our models of how structure formed in the early universe. Even more remarkably, GRBs help trace the universe's missing baryons, the ordinary matter that theory says should exist but telescopes can't find. About half of all atoms are thought to reside in diffuse gas between galaxies, too faint to detect directly. But when a GRB's light passes through these invisible reservoirs, it excites the gas molecules, causing them to emit secondary signals we can measure. It's like hearing an echo in a canyon. The burst's light bounces off hidden matter, revealing its presence indirectly. Every distant gamma-ray burst is effectively a probe sent billions of years ago, programmed to report back on conditions along its path. As we collect more of these cosmic messages, we're stitching together a three-dimensional map of the universe's large-scale structure, one brilliant flash at a time. They're not just explosions, they're the universe's own cartographers, scribbling its secrets in light across the void. Catching a gamma-ray burst in action is like trying to photograph lightning. You never know where or when the next strike will land. That's where satellites like NASA's Swift and Fermi come in, acting as the universe's lightning rods. These orbiting observatories are on constant patrol, their instruments primed to detect the slightest flicker of gamma rays from any corner of the sky. Swift, launched in 2004, is the cosmic equivalent of a lightning-fast paparazzo. The moment its burst alert telescope senses a GRB, the satellite can swivel in under a minute to train its X-ray and ultraviolet telescopes on the target, capturing the burst's fading glow before it vanishes forever. But Swift doesn't work alone. Fermi, its more sensitive counterpart, scans the entire sky every 3 hours with its large-area telescope, picking up even the faintest whispers of gamma radiation. Together, they form an unbeatable tag team. Swift's speed complements Fermi's precision, ensuring no burst goes unnoticed. What's truly remarkable is how these satellites transform raw detections into global scientific events. The instant Swift or Fermi spots a burst, automated systems blast out alerts to observatories worldwide, triggering a coordinated scramble among astronomers. Ground-based telescopes from Chile to Hawaii pivot toward the coordinates, racing to capture the afterglow in visible light, infrared, or radio waves before it fades. This real-time relay has revolutionized our understanding of GRBs. Before Swift, astronomers were often left chasing ghosts. Bursts would appear and disappear before follow-up observations could begin. Now, thanks to these satellites, we've caught hundreds of bursts in the act, dissecting their light curves and spectra like never before. The data has revealed subtle variations in brightness, hidden pulses within pulses, and even rare, ultra-long GRBs lasting nearly an hour. Perhaps most importantly, these satellites act as universal translators for GRBs. By correlating gamma-ray detections with follow-up observations, scientists can decode the burst's hidden messages, whether they signal the birth of a black hole, the collision of neutron stars, or something even more exotic. Every alert is a new chance to test theories about the most extreme physics in the cosmos, from relativistic jets to the behavior of matter at energies impossible to replicate on Earth. And the best part, this is just the beginning. New missions like the European Space Agency's Theseus, set to launch in the 2030s, promise to push GRB detection even further, probing deeper into the universe's youth. With each technological leap, these cosmic sentinels peel back another layer of mystery, turning fleeting flashes into lasting revelations about how the universe works at its most violent and spectacular. The true magic of gamma-ray bursts doesn't end with their initial explosion. It's what comes after that holds the real treasure. Like the embers of a colossal firework, GRBs leave behind a fading glow across multiple wavelengths, from X-rays to radio waves. This afterglow isn't just a cosmic encore. It's a goldmine of information, revealing secrets about the burst's origins that the initial flash could never tell us. Picture a lightning bolt striking a dark forest. For a split second, the flash illuminates everything, but it's the lingering glow that lets you see the trees, the terrain, the hidden details. That's precisely what afterglows do for astronomers. As the gamma ray bursts jet tears through space, it slams into surrounding gas and dust, creating shock waves that heat the material and produce this multicolored afterglow. X-rays come first, often detected within minutes, followed by visible light that can shine for days or even weeks. Radio waves, though fainter, sometimes persist for months, like distant echoes of the explosion. Here's the genius part. Each wavelength tells a different story. X-rays trace the fastest moving material in the jet's core, while optical light reveals the density and composition of the surrounding environment. Radio emissions, on the other hand, map the outermost edges of the explosion, showing how the blast interacts with interstellar material. By stitching these pieces together, astronomers can reconstruct the entire life cycle of the burst, from its violent birth to its gradual fade into darkness. One of the afterglow's most crucial roles is acting as a cosmic measuring tape. As the light travels through space, specific elements in its path absorb certain wavelengths, leaving dark fingerprint lines in the spectrum. The position of these lines shifts depending on how far the light has traveled, a phenomenon called redshift. By measuring this shift, scientists can calculate the burst's distance with astonishing precision. Some of the most distant GRBs ever found were pinpointed not by their initial gamma-ray flash, but by their afterglow's telltale redshifts. But afterglows do more than just measure distance. They expose the very fabric of the cosmos. In 2019, the afterglow of GRB 190114b revealed something extraordinary: signatures of iron and other heavy elements lingering near the burst site. This suggested the explosion occurred in a region already enriched by earlier generations of stars, painting a picture of a universe that was churning out complex chemistry far earlier than we thought. Even more remarkably, afterglows can act as backlights for the universe's hidden matter. When a burst's light passes through galaxies or gas clouds on its way to Earth, those structures imprint faint absorption features on the afterglow spectrum. It's like holding a flashlight behind a stained glass window. The light reveals the patterns in the glass. Scientists have used this trick to discover otherwise invisible galaxies and map the distribution of matter across billions of light years. What makes afterglows so invaluable is their persistence. While the gamma-ray flash might last mere seconds, the afterglow lingers long enough for telescopes worldwide to join the hunt. This global collaboration has turned random cosmic explosions into structured scientific events, with observers from Chile to Japan racing to capture the glow before it vanishes. Every afterglow is a puzzle box packed with clues about the universe's most extreme environments, and with each one we decode, we learn a little more about how the cosmos builds itself, one cataclysm at a time. Gamma-ray bursts are more than just brilliant flashes. They're cosmic birth announcements, signaling the violent arrival of newborn black holes. The most powerful long GRBs serve as delivery rooms for these gravitational monsters, born from the catastrophic collapse of stars dozens of times more massive than our Sun. Picture a dying giant, its core running out of nuclear fuel. As gravity overwhelms the star's outward pressure, the core implodes faster than the speed of sound, compressing matter so densely that not even light can escape. But here's where the magic happens. Not all that material gets swallowed. Some gets funneled into twin jets, narrow cosmic fire hoses blasting outward at over 99% the speed of light. These jets, packed with superheated plasma and magnetic energy, punch through the collapsing star's outer layers like bullets through tissue paper, and when they breach the surface, they unleash the gamma-ray burst we see from billions of light years away. This spectacular chain reaction is called the collapsar model, and it's reshaped how we understand stellar deaths. Unlike quieter black hole births where stars fade without fireworks, collapsars are the universe's most dramatic metamorphosis. A star's entire identity transforms in seconds. What was once a stable, shining sphere becomes an invisible singularity surrounded by a swirling disk of doomed matter, while its dying scream reverberates across the cosmos as a GRB. The jets themselves are physics laboratories beyond anything we could recreate on Earth, where matter moves so fast it warps time itself via relativistic effects. But how do we know this model holds up? The evidence comes in layers. First, we've caught long GRBs in galaxies actively forming massive stars precisely where short-lived stellar giants should be dying. Second, telescopes have spotted supernova accompanying some nearby bursts, confirming the stellar collapse connection. Most convincing was GRB 030329, where astronomers detected both the gamma-ray flash and the signature of nickel-rich debris from a supernova in the same location. It was like finding a smoking gun with fingerprints still warm. The collapsar process also solves a cosmic mystery: why some dying stars become quiet black holes while others explode as GRBs. The key lies in rotation. Stars that spin fast enough before death form whirling accretion disks around their newborn black holes, acting like particle accelerators that launch the jets. Slower spinning stars, their collapse is more chaotic, their energy dissipating without focus. This explains why GRBs are rare even among massive stars. Only those with the perfect combination of size, spin, and magnetic fields can produce these focused cosmic lasers. What's truly humbling is realizing we're witnessing the universe's recycling program in action. The same jets that create GRBs also spray heavy elements like gold and platinum into space at incredible speeds, seeding future generations of stars and planets. Every time we detect one of these bursts, we're seeing the moment a black hole not only forms but reshapes its corner of the cosmos, turning destruction into creation on an unimaginable scale. Not every gamma-ray burst puts on a visible light show. Some vanish into cosmic shadows, leaving astronomers baffled. These are the so-called dark bursts, events that blast out gamma rays but fail to produce the expected afterglow in optical wavelength. You'd think something capable of outshining galaxies would be impossible to miss, yet roughly 30% of GRBs observed by satellites like Swift show no visible trace despite intense searching. It's like hearing thunder but never seeing the lightning, a cosmic sleight of hand that's forced scientists to rethink what happens in the chaotic aftermath of these explosions. The leading theory points to thick cosmic dust as the culprit. Picture a GRB going off inside a dense stellar nursery where clouds of dust and gas swirl around newborn stars. When the burst's afterglow tries to shine through, those dust particles act like a celestial smokescreen, absorbing visible light while allowing longer wavelengths like infrared to pass through. This explains why many dark bursts still show up in infrared observations. Their light isn't gone, just transformed. Supporting this idea, astronomers have found dark GRBs preferentially occurring in galaxies teeming with star formation, where dust factories run at full capacity. But dust isn't the only suspect. Some dark bursts may originate in environments so extreme, their afterglows get smothered by the very conditions that spawn them. Take GRB 060614, a burst that defied expectations. Despite occurring relatively nearby, its afterglow was nearly invisible until infrared telescopes picked up a faint signal. The culprit, a cocoon of gas so dense, it absorbed the visible light, completely evidence that the burst's progenitor star might have been shrouded in material ejected shortly before its death. This suggests some massive stars go through violent pre-explosion convulsions, cloaking themselves in their own debris before their final act. The plot thickens when considering an even stranger possibility that some dark bursts might be signaling entirely new physics. A handful of events show no afterglow in any wavelength, not just visible light. These could represent GRBs occurring at such tremendous distances that the universe's expansion has stretched their light beyond detection, or perhaps jets pointed almost directly away from us, offering only a glancing view of their energy. Most intriguing are theories involving exotic stellar remnants like magnetars, whose intense magnetic fields might channel energy in ways that suppress traditional afterglows. What makes dark bursts so valuable is their refusal to fit neatly into boxes. Every time we catch one, it forces us to question assumptions about how GRBs interact with their surroundings, and by extension, how matter behaves under conditions we can't replicate on Earth. They're reminders that the universe still holds surprises, even in phenomena we think we understand. As telescopes grow more sensitive, these shadowy explosions may finally step into the light, revealing secrets about the dusty corners of the cosmos where stars are born and black holes wake. Every piece of gold jewelry, every platinum wedding band, even the uranium in nuclear reactors, they all share a cosmic origin story written in the fury of gamma-ray bursts. Specifically, the short bursts born from neutron star collisions are nature's ultimate alchemists, forging heavy elements under conditions so extreme they dwarf anything in a laboratory. Here's how it works. When two neutron stars, the dense, city-sized remnants of dead stars, spiral into each other, their merger unleashes a tempest of nuclear physics. The outer layers of these stars, packed with neutrons like overstuffed atomic nuclei, get flung into space at relativistic speeds. In this chaotic cloud, atomic particles crash together with such force that they capture free neutrons almost instantly, a process called rapid neutron capture, or the R process. This transforms ordinary matter into exotic, heavy elements like gold, platinum, and uranium, elements too hefty to form in the cores of ordinary stars. The proof arrived spectacularly in 2017 with GW170817, the first neutron-star merger detected in both gravitational waves and light. As telescopes raced to observe the aftermath, they found something groundbreaking: the infrared glow of newly minted heavy elements, totaling roughly an Earth's mass worth of gold and platinum alone. That single event produced more precious metals than all the mines in human history combined. It confirmed what theorists had long suspected, that these violent cosmic smash-ups are the universe's primary forges for the heaviest elements in the periodic table. This changes how we see Earth's own treasure trove. The gold in your ring or the platinum in a catalytic converter likely began as debris from a neutron star collision that occurred billions of years ago, before our solar system even existed. Those atoms were scattered across interstellar space, eventually mixing with the gas cloud that formed our sun and planets. It means we're literally wearing pieces of celestial cataclysms, remnants of explosions so powerful they briefly outshone entire galaxies. But here's where gamma-ray bursts add another layer. Not all neutron star mergers create detectable GRBs, only those with jets pointed directly at Earth. That suggests the events we've witnessed might be the tip of an iceberg, with many more mergers happening unseen. Each one seeds its host galaxy with these heavy elements, enriching future generations of stars and planets. Some estimates suggest it would take just a handful of neutron star collisions per galaxy every million years to account for all the R process elements we observe. What's truly staggering is the timescale. The gold in your pocket might have spent billions of years drifting between stars before getting trapped in a molecular cloud, compressed into Earth's crust, and finally extracted by human hands. These elements are more than just metals, they're cosmic relics, each atom a silent witness to one of the universe's most violent and beautiful transformations. And thanks to gamma-ray bursts, we can trace their origins back to the very explosions that made them. Gamma-ray bursts may dazzle us from across the universe, but their true destructive power becomes terrifyingly clear if one were to happen in our cosmic backyard. A GRB striking Earth from within our own galaxy wouldn't just be a light show. It could rewrite the history of life itself. the danger lies in two lethal punches: an initial blast of gamma rays moving at light speed, followed by a slower but equally devastating wave of high-energy particles. For context, astronomers estimate that a burst occurring within 6,000 light-years of Earth would deliver as much energy to our atmosphere in seconds as the Sun does over hundreds of thousands of years. The first strike, the gamma rays themselves, would act like a cosmic microwave, ionizing the upper atmosphere and triggering Chinese letter that break apart ozone molecules. Our planet's protective ozone layer, which shields life from the Sun's ultraviolet radiation, could be depleted by 50% or more in a matter of weeks. The consequences would mirror the worst-case nuclear winter scenarios, but with an added twist. Prolonged exposure to unfiltered UV radiation would devastate ecosystems. Plankton populations, the foundation of the marine food chain, could collapse, triggering catastrophic ripple effects. Land plants would suffer radiation burns, crippling agriculture worldwide. But the nightmare doesn't end there. Hours to days after the initial flash, a second wave of charged particles would arrive, accelerated by the burst shockwaves. This cosmic storm would bathe the planet in prolonged radiation, further damaging the atmosphere and potentially inducing mutations across species. Paleontologists have even speculated that a nearby GRB might explain some of Earth's past mass extinctions, particularly the Ordovician event 450 million years ago, which wiped out 85% of marine species. The timing aligns with evidence of sudden ozone depletion and a mysterious surge in UV-sensitive fossil mutations. Here's the chilling part: our galaxy hosts all the ingredients for such a catastrophe. Regions like the Carina Nebula, packed with massive stars destined to collapse as GRBs, lie well within the danger zone. Statistically, where overdue calculations suggest Earth should get hit by a lethal GRB every few 100 million years. The only silver lining: the odds favor the jet being narrow. Unless we're directly in its path, most of the energy would miss us. But with thousands of potential GRB progenitors in our galaxy, it's less a question of if than when another nearby star goes supernova in just the wrong way. What makes this threat uniquely unsettling is our helplessness against it. Unlike asteroids, we can't deflect gamma-ray bursts. Unlike solar flares, we can't harden our grids against them. Our best hope lies in early detection, monitoring unstable giant stars that might soon collapse. If we spotted a precursor event, humanity might have mere hours to shield infrastructure or seek underground refuge. Yet even that warning would come with sobering uncertainty, as we'd have no way to measure the jet's precise direction until the gamma rays actually arrive. Ultimately, GRBs remind us that we exist at the universe's mercy. Their distant beauty masks a destructive potential that, if aimed our way, could undo eons of evolution in an instant. Yet this vulnerability also underscores how rare and precious Earth's window of habitability truly is. A fleeting cosmic alignment where life can flourish between the universe's periodic tantrums. On August 17, 2017, the universe handed scientists a gift unlike any other. A cosmic event so perfectly timed, so rich in data, it felt almost orchestrated. That day, gravitational wave detectors LIGO and Virgo picked up ripples in spacetime from a collision 130 million light-years away. But this wasn't just any merger. For the first time in history, the subtle warping of spacetime came with an electromagnetic counterpart. A short gamma-ray burst detected by NASA's Fermi satellite just 1.7 seconds later. GRB 170817 wasn't just another burst. It was the Rosetta Stone astronomers had been waiting for, confirming decades of theories about the origins of short GRBs in a single, spectacular observation. The significance of this dual detection can't be overstated. Until that moment, the connection between neutron star mergers and short gamma-ray bursts had been purely theoretical. Models suggested these ultra-dense stellar remnants could produce narrow, energetic jets when they spiraled into each other, but without direct evidence, it remained an elegant guess. GRB 170817 changed everything. The gravitational wave signal revealed the precise masses of the colliding objects, two neutron stars totaling about 2.7 times the Sun's mass, while the gamma-ray burst confirmed that such collisions really do produce the relativistic jets we observe across the universe. What made this event truly exceptional was the wealth of follow-up data. Within hours, telescopes across the globe swiveled toward the source, capturing something never seen before: a kilonova, the radioactive glow of freshly forged heavy elements. The afterglow's spectrum bloomed with signatures of gold, platinum, and uranium, proving neutron star mergers are cosmic alchemists, transforming ordinary matter into the periodic table's heaviest elements through the rapid neutron capture process. This single observation solved two mysteries at once: the origin of short GRBs and the cosmic factories behind Earth's precious metals. But the serendipity didn't stop there. The burst itself was oddly faint for its distance, emitting only about 1% the energy of typical short GRBs. This led to a breakthrough realization: we were seeing the event from an oblique angle, slightly off-axis from the jet's core. For the first time, astronomers could study how these jets behave when not pointed directly at Earth, revealing their structure isn't uniform but layered, like a lighthouse beam with a bright center and dimmer edges. Perhaps most remarkably, GRB 170817 showcased the power of multi-messenger astronomy, the ability to study cosmic events through different messengers like light, gravitational waves, and particles. This one collision produced signals across the spectrum, from gamma rays to radio waves, while also shaking the fabric of spacetime itself. It was as if the universe had handed scientists a textbook example, perfectly timed to validate theories just as advanced detectors came online. The legacy of this lucky break continues to reshape astrophysics. It proved that neutron star mergers are laboratories for extreme physics, where matter gets compressed beyond nuclear densities and magnetic fields reach strengths 1 trillion times Earth. It also gave us a new way to measure cosmic distances. By comparing gravitational wave amplitudes with electromagnetic observations, astronomers could calibrate the universe's expansion with unprecedented precision. Yet for all its answers, GRB 170817 left tantalizing questions. Why was its jet so narrow compared to models? What role do magnetic fields play in shaping these outflows? And how often do such mergers produce detectable gamma rays? Each puzzle piece reminds us that even when the universe hands us a gift, it's often wrapped in layers of mystery, waiting for the next breakthrough to unravel. The jets produced by gamma-ray bursts don't just move fast, they rewrite the rules of speed itself. Clocking in at 99.99% the speed of light, these narrow beams of plasma and radiation are among the fastest naturally occurring objects in the universe. To grasp that velocity, imagine a particle racing around Earth's equator. At this speed, it could complete the entire 25,000-mile loop in just a fraction of a second, 7 times over before you could blink. That's not just breaking the sound barrier, it's shattering the cosmic speed limit, pushing the boundaries of what physics allows for matter. What makes this even more mind-bending is how these jets maintain their extreme velocity. Unlike rockets, which rely on continuous thrust, GRB jets are born with their staggering speed thanks to the unimaginable forces at play during a star's collapse or neutron star collision. Picture a cosmic hose powered by a black hole's gravity. Material spiraling into the abyss gets funneled into magnetic fields so intense, they act like particle accelerators the size of solar systems. This slingshots particles outward with such energy that time dilation kicks in dramatically. For particles in the jet, time slows to a crawl relative to the outside universe. A minute for them could be years for us, a real-world example of Einstein's theory of relativity in action. The consequences of this speed are twofold. First, it explains why GRBs can be seen across such vast distances. Their light doesn't just travel, it screams through the cosmos, barely dimmed by the expanding universe. Second, the velocity creates what's called relativistic beaming, where radiation gets concentrated into the direction of motion like headlights on a speeding train. This effect amplifies the burst's brightness, making it appear even more luminous than it truly is if you're in the beam's path. Miss that narrow cone by even a few degrees and you'd see nothing, a cosmic strobe light illuminating only a sliver of the universe. Here's where it gets counterintuitive. Despite moving almost indistinguishably close to light speed, these jets aren't breaking physics. They're riding the razor's edge of possibility, where energy converts to velocity with near-perfect efficiency. Each proton in that jet carries kinetic energy billions of times greater than what our most powerful particle colliders can produce. If a single grain of sand moved at this speed, it would pack the punch of a nuclear bomb. Now scale that up to the jet's full mass, often equivalent to an entire planet's worth of material, and you begin to understand why GRBs can outshine galaxies. This blistering speed also solves a mystery about how GRB jets punch through their surrounding stars. A collapsing star's outer layers should, in theory, smother any explosion before it escapes. But at 99.99% light speed, these jets act more like lasers than traditional explosions, drilling through stellar material with pinpoint precision before erupting into open space. Simulations show the leading edge of the jet heat surrounding gas to billions of degrees, creating a self-sustaining tunnel that lets the rest of the beam follow virtually unimpeded. It's nature's ultimate blowtorch, fueled by raw velocity and physics stretched to its limits. Yet for all their power, these jets are fleeting. Their extreme speed means they dissipate quickly as they plow into interstellar gas, like a motorcycle hitting a wall of fog. Within days or weeks, the jet slows enough that its light fades from view, but not before delivering an unforgettable performance, one where the universe itself becomes the stage for the fastest show in existence. Some gamma-ray bursts defy expectations by appearing in the cosmic equivalent of nowhere vast, empty regions far from any visible galaxy. These lonely GRBs present astronomers with a head-scratching mystery. How can the universe's most energetic explosions occur in places where their presumed stellar progenitors shouldn't exist? Take GRB 070125, which flared up in 2007. When telescopes swiveled to its location, they found only darkness, no host galaxy visible, not even with the deepest observations from Hubble. The burst sat isolated in intergalactic space, like a single firework detonated in an empty desert. The theories to explain these cosmic orphans are as fascinating as the mystery itself. One possibility involves gravitational kickback when a massive star collapses into a black hole. The asymmetric explosion can literally punt the newborn black hole across space at speeds exceeding 1 million miles per hour. Computer simulations show these kicked black holes could travel hundreds of thousands of light years from their birth galaxies before their jets produce a gamma ray burst millions of years later. Imagine a bullet fired from a galactic gun. By the time it goes off, the shooter is long gone from view. Another explanation peels back the layers of cosmic camouflage. Some apparently hostless GRBs might actually originate in ultra-faint dwarf galaxies, so dim they evade detection even with our most powerful telescopes. These ghostly galaxies, barely held together by dark matter, could form massive stars but lack the luminosity to be seen across intergalactic distances. Supporting this idea, a few lonely bursts later revealed faint smudges of light upon re-examination with upgraded instruments, like spotting a lone cabin's embers after your eyes adjust to the night. The most exotic theory suggests some GRBs could come from stars flung into the void during galactic collisions. When galaxies merge, their gravitational chaos can eject entire star clusters at tremendous speeds. A massive star making this cosmic ejection might explode far from its birthplace, leaving no visible trace of its original home. This would make certain GRBs intergalactic castaways, their flashes signaling not just a star's death but its long exile from the stellar community. What makes these outliers scientifically valuable is their ability to test the boundaries of our understanding. If lonely GRBs come from kicked black holes, they offer a natural laboratory for studying recoil physics at scales impossible to replicate. If they're tied to invisible dwarf galaxies, they could help solve the missing satellite problem, the puzzling shortage of small galaxies predicted by dark matter models. Each unexplained burst forces us to reconsider how stars form and die in the universe's most neglected neighborhoods. The next generation of telescopes may finally solve this cosmic whodunit. Instruments like the James Webb Space Telescope can peer deeper into these empty patches of sky, potentially revealing the faintest galactic fingerprints. Until then, these solitary flashes serve as reminders that the universe still holds surprises even in its emptiest corners, where the rules we take for granted might not always apply. Gamma-ray bursts act as cosmic historians, preserving records of when and where stars were born in the universe's turbulent early years. Unlike traditional telescopes that struggle to spot faint galaxies from billions of years ago, GRBs cut through the darkness with their explosive brilliance, pinpointing stellar nurseries across space and time. Their distribution tells a remarkable story, one where the universe hit its peak star making stride roughly 10 billion years ago, churning out new suns at a rate 20 times faster than today. Imagine the early cosmos as a factory floor running at maximum capacity. Galaxies back then were smaller but far more active, crammed with dense clouds of pristine gas perfect for forging stars. GRBs from this era serve as timestamps, their redshifts revealing exactly when these stellar factories were operating. By tallying bursts from different cosmic epochs, astronomers discovered a clear pattern. The frequency of long GRBs, those linked to massive star deaths, peaks around redshift 3, corresponding to a time when the universe was just 2 billion years old. This surge aligns perfectly with other evidence of cosmic noon, that golden age of star formation when galaxies burned bright with youthful energy. But GRBs add something unique to this picture. They expose the darkest corners of star formation that other probes miss. Regular surveys tend to spot only the brightest galaxies, missing smaller or dust-choked ones where stars still form quietly. GRB, however, don't discriminate. Whether their host galaxy is a brilliant spiral or a faint dwarf, the burst shines through all the same. This unbiased sampling revealed a surprising truth. Much of the universe's star birth happened in humble, low-mass galaxies that would otherwise fly under the radar. The composition of these ancient bursts adds another layer to the story. Spectra from their afterglows show fewer heavy elements than modern GRBs, reflecting the early universe's simpler chemistry. This pristine environment allowed stars to grow to monstrous sizes, far larger than anything in today's metal-rich galaxies. When these giants died as GRBs, their explosions seeded space with the first heavy elements, gradually enriching the cosmos for future generations of stars and planets. Perhaps most astonishing is how GRBs help solve the puzzle of when the first stars switched on. The farthest known burst, GRB 090423, erupted when the universe was just 630 million years old, proof that massive stars were already living fast and dying young in that primordial darkness. Without these flashes, we might never have known how quickly the cosmos got to work after the Big Bang, transforming emptiness into light. Every distant gamma-ray burst is more than a cataclysm. It's a birth certificate for the universe's stellar population. By mapping their distribution, we've reconstructed the rise and fall of star formation across cosmic history, tracing how galaxies evolved from chaotic, star-making machines into the more sedate neighborhoods we see today. And with each new burst discovered, we add another piece to this billion-year timeline, watching as the universe grows up one explosion at a time. Gamma-ray bursts don't always play by the rules. Sometimes they deliver surprises that force scientists to rethink their categories. Take GRB 2008-26A, a record-breaking burst that lasted just 0.6 seconds, making it the shortest gamma-ray burst ever detected. At first glance, it fit neatly into the short GRB category, which typically lasts under 2 seconds and stems from neutron-star collisions. But when astronomers dug deeper, they found something perplexing. This fleeting explosion had all the hallmarks of a long GRB, the kind produced by collapsing massive stars. It was like finding a hummingbird with the skeletal structure of an eagle, a cosmic contradiction that blurred the lines between two supposedly distinct classes of explosions. This anomaly sent researchers scrambling for explanations. One theory suggests GRB 2008-26 was essentially a long GRB that got cut short. Picture a massive star collapsing into a black hole. Its death throws launching jets as usual. But this time, the star's outer layers were either too thin or the jets too weak to sustain the typical multi-second outburst. The result, a burst that flickered out almost immediately, mimicking the brief flashes of neutron star mergers. Supporting this idea, follow-up observations revealed a faint supernova signature days later, a telltale sign of a massive star's death. It was the smoking gun that proved this burst, despite its brevity, belonged to the long GRB family. The implications ripple across astrophysics. If short-lived bursts can emerge from collapsing stars, it means our classification system, based solely on duration, might be oversimplifying a far messier reality. GRBs could exist on a spectrum, with some massive stars producing failed long bursts that masquerade as short ones. This reshapes how we interpret past observations, especially those without follow-up data to confirm their origins. Suddenly, bursts once assumed to be neutron star mergers might need re-evaluation, their true nature hidden behind deceptive timing. What makes GRB 2008-26 so valuable is its rarity. Most short bursts lack supernova connections, making this outlier a critical clue. It hints at an unseen population of borderline cases, bursts that straddle categories, challenging our neat divisions. Future detections could reveal whether this was a fluke or a sign that the universe enjoys bending its own rules, reminding us that even the most violent cosmic events refuse to be pigeonholed. Gamma-ray bursts pull off one of the universe's most convincing magic tricks. Their jets appear to break physics by moving faster than light. This mind-bending illusion, called superluminal motion, doesn't actually defy Einstein's cosmic speed limit. Instead, it's a cosmic sleight of hand caused by the jet's extreme velocity and their angled trajectory toward us. Here's how the trick works. When a GRB's jet barrels through space at over 99.9% light speed, nearly head-on toward Earth, the time delay between light emitted from different points along the jet gets compressed. Imagine a cosmic lighthouse where the light beam is almost parallel to your line of sight. Because the jet's material is racing so close to light speed, new emissions from the jet's tip nearly keep pace with the older light it emitted moments earlier from its base. The result, from our vantage point, the jet's features seem to crawl outward faster than light, like a cosmic zoom effect gone wild. The first time astronomers measured this phenomenon in GRB jets, it caused a stir. Observations of GRB 930221 showed bright knots in the jet, apparently separating at 7 times light speed. But relativity wasn't overturned, just outsmarted by geometry. This superluminal illusion only happens when the jet points almost directly at us, its motion foreshortened like watching a bullet fired straight toward your face. The same physics creates similar illusions in quasars and pulsars, but GRBs provide the most dramatic examples because their jets are faster and more focused. What's wild is that this illusion actually helps scientists measure the jet's true speeds and angles. By tracking how quickly features appear to move across the sky and comparing that to the burst's redshift, astronomers can calculate the jet's real velocity and orientation. It's like using a visual glitch to reverse engineer the universe's coding. Some jets, like those from GRB 990123, revealed angles less than 5 degrees off our line of sight, explaining both their extreme brightness and their apparent light speed defiance. This quirk of perspective also solves a long-standing GRB mystery: why we detect so few of them despite their frequency. Only jets aligned within a few degrees of Earth produce the characteristic bright flash we recognize. The rest, firing off into empty space at similarly ridiculous speeds, go unnoticed, their energy wasted on the cosmic void. So when we witness one of these superluminal illusions, we're not just seeing physics pushed to its limits, we're catching the universe in a rare moment where its angles and speeds conspire to create the ultimate cosmic mirage. Far from breaking the rules, these light-speed charades actually confirm Einstein's theories in the most extreme laboratory imaginable. The jet's behavior precisely matches relativistic predictions, proving once again that even when the universe seems to cheat, it's still playing by the same fundamental rules, just with a flair for dramatic presentation. Every superluminal GRB is a reminder that in astrophysics, sometimes the most impossible-seeming feats are just the universe showing off its mastery of angles and velocities. On October 9, 2022, gamma-ray detectors around the world lit up like never before. GRB 221009, a quickly nicknamed the BOT for brightest of all time, wasn't just another cosmic explosion. This burst unleashed so much energy in its first few seconds that it temporarily blinded sensitive space telescopes, overwhelming their detectors like a camera pointed directly at the sun. Preliminary measurements suggested it carried enough punch to outshine the entire Milky Way galaxy by a factor of 10 million. For nearly 10 hours, the afterglow remained brighter than most supernova, an endurance unmatched in GRB history. What made this particular burst so extraordinary wasn't just its raw power, but where it came from. Unlike most distant GRBs that originate billions of light-years away, the BOT erupted a mere 2 billion light-years from Earth, cosmically speaking, right in our neighborhood. That proximity magnified its effects, giving astronomers an unprecedented close-up view of nature's most powerful particle accelerators in action. Satellite readings later revealed its gamma-ray photons carried energies exceeding 18 tera-electronvolts, enough to power a small city if harnessed, all packed into individual light particles. Theories about its origins point to something far more exotic than a typical collapsing star. While most long GRBs stem from massive stars going supernova, the BOT's energy profile suggests something rarer. A magneto-rotational explosion, where a rapidly spinning star with an ultra-strong magnetic field collapses. Picture a cosmic dynamo the size of a solar system, its magnetic fields twisted tighter than a coiled spring until they finally snap, channeling nearly all the star's dying energy into those focused jets. This mechanism could explain why the burst's afterglow showed unusual polarization patterns, hinting at magnetic fields trillions of times stronger than Earth's guiding the explosion. Even more intriguing were the secondary effects. The burst's gamma rays ionized Earth's upper atmosphere more powerfully than a solar flare, despite originating halfway across the universe. Its light also illuminated normally invisible dust clouds in our own galaxy, creating eerie X-ray echoes that mapped hidden structures between stars. For weeks afterward, telescopes caught the afterglow interacting with previously unseen gas filaments in intergalactic space, turning the burst into an impromptu cosmic flashlight. What the BOT ultimately revealed was how much we still don't understand about these extreme events. Standard GRB models struggled to account for its longevity and multi-wavelength behavior, forcing physicists to revisit decades-old assumptions about jet formation and energy transfer. Some theorists even speculate it might represent a new subclass of hybrid explosions where stellar collapse meets the physics of magnetars and black holes in ways we've never witnessed before. One thing's certain, when the next BORT arrives, whether in years or centuries, astronomers will be ready with far better tools to decode its secrets. Until then, this record-breaking burst stands as a humbling reminder of the universe's capacity to surpass even our wildest expectations. Gamma-ray bursts aren't just cosmic spectacles, they might be the universe's ultimate reset buttons, wiping clean entire swaths of real estate where life could otherwise take root. This grim possibility, known as the GRB sterilization hypothesis, suggests these explosions could be silently shaping the distribution of intelligent life across galaxies by periodically scouring planets clean of complex organisms. The math is sobering. A single nearby burst within 6,000 light-years could deliver enough radiation to strip Earth's ozone layer for years, bathing the surface in deadly ultraviolet radiation. Multiply that across billions of years and galaxies, and you're looking at a potential cosmic filter, one that might explain why the universe seems so quiet despite its staggering number of planets. The sterilization scenario plays out in three brutal waves. First comes the initial gamma-ray flash, ionizing the upper atmosphere and triggering chemical reactions that dismantle ozone molecules. Next arrives the ultraviolet onslaught, normally blocked by that ozone shield, now pouring unfiltered onto the surface. Simple marine life and surface-dwelling organisms would face radiation doses hundreds of times higher than normal, causing mass mutations and cell damage. The final blow comes from secondary effects: acid rain from nitrogen oxides in the irradiated atmosphere, global cooling as smog blocks sunlight, and ecosystem collapse as food chains unravel. Paleontologists note that Earth's Ordovician extinction 450 million years ago, which wiped out 85% of marine species, aligns suspiciously with evidence of sudden ozone depletion. While no smoking gun GRB has been identified, the timeline fits eerily well. What makes this hypothesis especially chilling is its implications for the Milky Way's habitable zones. Our galaxy's suburbs regions, like our solar system's location about halfway from the center, might be uniquely vulnerable. The crowded galactic core has more GRB producing massive stars, but also more supernova clearing turbulence that disperses stellar nurseries. The outer reaches, meanwhile, lack enough heavy elements to form Earth-like planets in the first place. That leaves a Goldilocks annihilator ring where GRBs are frequent enough to pose a threat but sparse enough that civilizations might occasionally slip through unscathed. Yet there's a twist to this cosmic horror story. GRBs might paradoxically enable life as well as destroy it. The same heavy elements forged in these explosions, carbon, oxygen, iron, are essential building blocks for planets and biology. Some models suggest early GRBs could have jump-started life by delivering phosphorus, a crucial ingredient for DNA, to primordial Earth via asteroid impacts laden with burst debris. Furthermore, the threat of periodic sterilizations might accelerate evolution by forcing species to adapt or perish, potentially hastening intelligence in survivors. It's a brutal cosmic balancing act: too many GRBs and life gets snuffed out, too few, and the chemistry for complexity never arrives. The most profound question raised by this hypothesis is whether we're living on borrowed time. Statistical analyses suggest Earth should experience a lethal GRB every few 100 million years, meaning we're statistically overdue. Our saving grace might be pure luck. The jet's narrow beams mean most bursts miss us entirely. But for civilizations on planets less fortunate, the universe might be an endless cycle of budding life and sudden silence. That could explain the Fermi paradox's great silence. Advanced cultures might bloom only briefly before the next gamma-ray scythe swings through their galactic neighborhood. As telescopes like James Webb search for biosignatures on exoplanets, they might unknowingly be hunting in GRB shadowlands, worlds temporarily between cosmic catastrophes. The grim reality is that gamma-ray bursts could be the universe's ultimate gardeners, pruning the tree of life just as it begins to bear fruit. Yet in that devastation lies a strange hope. If life and intelligence can survive this intermittent sterilization, it proves resilience against even the universe's most violent whims. Every civilization we ever discover or become might carry the scars of near misses with these celestial reapers. Some of the most bizarre gamma-ray bursts in the cosmic record might owe their existence to nature's ultimate magnetic monsters, magnetars. Imagine a neutron star, already one of the densest objects in existence, then crank its magnetic field up 1,000 trillion times stronger than Earth's. That's a magnetar, a stellar corpse so magnetically charged, its field could strip the information from every credit card on our planet from halfway across the galaxy. When these cosmic powerhouses misbehave, they don't just emit energy, they rewrite the rules of what we thought possible for GRBs. Take GRB 2004-416, a burst that defied classification. Unlike typical GRBs that fade within minutes, this one kept flickering for over 6 minutes with strange, periodic pulses. The culprit, a newborn magnetar struggling to stabilize its unimaginably twisted magnetic fields. As these fields snapped and reconnected, a process called magnetic reconnection, they unleashed focused beams of gamma rays in rhythmic outbursts like a cosmic lighthouse stuck in overdrive. This wasn't the clean jet of a collapsing star, but the tortured scream of magnetism itself unraveling. What makes magnetar-powered bursts so distinctive is their magnetic fingerprints. Regular GRB jets rely on raw kinetic energy particles blasting outward at near light speed. Magnetar flares, by contrast, channel their energy through magnetic field lines so contorted, they act like particle accelerators the size of solar systems. The result, gamma rays with unusual polarization patterns and energy distributions that stand out like flares in the night. Some bursts, like the bizarre GRB 070610, even show telltale X-ray bumps in their afterglows, the signature of a magnetar's magnetic field dumping energy into surrounding debris long after the initial explosion. The numbers involved stretch credibility. A typical magnetar's field measures around 10 to the 15th Gauss, strong enough to distort the orbits of electrons inside atoms from thousands of miles away. When these fields fracture during what's called a starquake, the energy release can outshine our sun for months in just a fraction of a second. In 2004, satellites detected a magnetar flare from 50,000 light-years away that still managed to briefly ionize Earth's upper atmosphere, a literal space weather event originating halfway across the galaxy. Yet for all their power, magnetar GRBs might solve a long-standing mystery, where some of the universe's shortest yet most energetic bursts come from. Traditional neutron star mergers can't easily explain millisecond GRBs packing such incredible punch, but a magnetar's magnetic collapse that could deliver both the brevity and the intensity in one terrifying package. It's the difference between a gasoline fire and a shaped charge, both explosive, but one concentrates its fury with pinpoint precision. Perhaps most astonishing is how magnetars blur the line between different cosmic phenomena. The same physics driving their gamma-ray outbursts might also power fast radio bursts, those mysterious intergalactic radio pulses we're still struggling to understand. Some theorists even speculate that the rarest GRBs could come from hypermagnetars, objects with fields so intense they temporarily surpass known physics before collapsing into black holes. Every unusual burst pattern we detect could be another piece of this magnetic puzzle, showing us how the universe plays with forces we can barely comprehend. What magnetar GRBs ultimately teach us is that the cosmos has more than one way to scream across the void. Whether through gravitational collapse, stellar collisions, or magnetic apocalypses, the universe finds endless variations on the theme of annihilation, each one leaving behind clues written in light for those who know how to read them. And as we uncover more of these magnetic mavericks, we're not just cataloging explosions, we're mapping the limits of how matter behaves when pushed beyond all reason. Gamma-ray bursts aren't just cataclysmic events, they're the universe's own rulers, helping astronomers measure cosmic distances with surprising precision. While redshift has long been the go-to tool for gauging how far light has traveled, GRBs offer something even more versatile, built-in brightness markers in their light curves that function like cosmic yardsticks. Think of it like recognizing a familiar face in a crowd. Certain features in a burst's afterglow behave predictably enough that scientists can estimate its distance even without redshift data. This makes them potential standard candles, much like how Cepheid variables and Type Ia supernova revolutionized our measurement of the nearby universe. The secret lies in the correlation between a GRB's luminosity and its temporal structure, specifically how quickly its light fades. After the initial blast, the afterglow follows a distinct pattern, a rapid drop in brightness followed by a smoother decline. The timing of this transition, known as the break time, relates directly to the burst's total energy output. Brighter bursts tend to have later breaks, while fainter ones fade more quickly. By analyzing this relationship across hundreds of observed GRBs, astronomers have calibrated empirical formulas that link the observed brightness to intrinsic luminosity. It's as if each burst carries a built-in energy receipt, allowing us to backtrack how far its light traveled. What makes this method revolutionary is its reach. While supernova as standard candles max out around redshift 1.7, roughly 10 billion light-years, GRBs can be detected at redshifts beyond 9, probing eras when the universe was less than 5% of its current age. This extends the cosmic distance ladder into realms otherwise inaccessible, offering a way to cross-check redshift measurements and test the universe's expansion rate during its infancy. One groundbreaking study used GRB 050824, a burst at redshift 6.3, to confirm the presence of dark energy's influence even in the early cosmos, something supernova alone couldn't achieve. Yet GRBs aren't perfect standard candles. Their diversity means tighter margins of error require large samples, and factors like jet geometry or surrounding dust can muddy the signal. That's where a multi-relation comes in, a correlation between a burst's peak energy and its total energy output, helping filter out outliers. When combined with other spectral and temporal features, these relationships sharpen GRBs into precision tools. Future missions like the European Space Agency's Theseus aim to catalog thousands more bursts, refining these correlations to rival supernova in reliability. The implications stretch beyond mere distance measurement. If perfected, GRB standard candles could independently verify contentious values like the Hubble constant, currently mired in a discrepancy between local and early universe measurements. They might also reveal whether dark energy's strength has changed over time, a question central to understanding the cosmos's ultimate fate. Every burst that lights up the sky isn't just a fleeting spectacle, it's a potential keystone in the architecture of cosmic distances, helping us map the universe's expansion with ever greater confidence. And in a cosmos with so much left to measure, that's a tool worth its weight in gamma rays. GRB 060218 wasn't just another gamma-ray burst, it was a cosmic ghost, flickering into view only to vanish in ways that left astrophysicists utterly baffled. Detected by NASA, a Swift satellite in 2006, this burst defied every expectation, stretching its afterglow for nearly 2,000 seconds, an eternity by GRB standards. But what made it truly bizarre was how it faded. Not with the predictable decline of most bursts, but in erratic pulses, as if something unseen was tampering with its light. This wasn't just an explosion, it was a cosmic magic trick, challenging everything we thought we knew about how these events behave. At first glance, GRB 060218 seemed ordinary enough. Its gamma-ray emission lasted a typical 30 seconds, and its redshift placed it a comfortable 440 million light-years away, practically next door by cosmic standards. But then the afterglow began acting strangely. Instead of smoothly dimming, it flared unpredictably across X-ray and optical wavelengths, brightening and fading like a candle fighting a draft. Telescopes caught eerie oscillations in its light curve, as if the burst's energy was being siphoned away or reflected by invisible structures. The usual suspects, dust absorption, jet instabilities, failed to fully explain the behavior. It was like watching a shadow puppet show where the puppeteer kept changing the script. The leading theory points to a cosmic echo chamber. The burst's jets might have encountered dense, clumpy material around the progenitor star, perhaps ejected in violent pre-explosion outbursts. As the jets plowed through this debris, shockwaves could have created secondary emission regions, each contributing its own flickering afterglow component. Imagine shining a flashlight through a room full of mirrors. The original beam gets lost in a maze of reflections. Similarly, GRB 060218's light may have scattered off circumstellar wreckage, turning a straightforward afterglow into a hall of illusions. What makes this ghostly burst so scientifically valuable is how it exposes gaps in our models. Standard GRB theories assume relatively clean environments around collapsing stars with jets traveling through uniform gas. But GRB 060218 suggests some progenitors die messy deaths, surrounded by chaotic shells of previously ejected material. This aligns with growing evidence that massive stars undergo violent convulsions in their final years, shedding layers unpredictably before their final collapse. If common, these pre-burst eruptions could explain other anomalous afterglows, bursts that fade too slowly or with odd color changes, as if something unseen is sculpting their light. Even more intriguing is the burst's possible connection to a rare supernova subtype. Days after detection, telescopes spotted a faint supernova SN 2006 Aj at the same location. But unlike typical supernova linked to GRBs, this one was peculiarly dim, suggesting the star might have been unusually low in mass or heavily shrouded in dust. Some theorists speculate GRB 060218 represents a hybrid event, not quite a standard collapsar, not quite a neutron-star merger, but something in between. Perhaps the death throes of a magnetar-progenitor or a star caught in the act of transitioning into an exotic compact object. The legacy of this ghost burst lingers in modern GRB research. It taught astronomers to expect the unexpected, proving that these cosmic explosions can wear many masks. Every new anomalous afterglow, whether flickering, fading too slowly, or showing bizarre spectral features, gets compared to GRB 060218, testing whether it's a one-off oddity or part of a hidden population of similarly strange events. And as detectors grow more sensitive, we may finally unmask the mechanisms behind these cosmic illusions, revealing whether they're mere curiosities or signposts to entirely new physics lurking in the darkness between the stars. Gamma-ray bursts don't just vanish without a trace. Their explosive energy lingers in their host galaxies, reshaping cosmic neighborhoods long after the initial flash fades. These ultra-powerful jets act like interstellar blowtorches, heating vast clouds of star-forming gas to millions of degrees, effectively pressing pause on stellar birth cycles for millions of years. Imagine a young galaxy bustling with stellar nurseries, its cold molecular clouds condensing into new suns until a GRB erupts, flooding the region with enough radiation to send those delicate structures boiling away into diffuse, unusable plasma. This process, known as feedback, reveals how the most violent events in the universe paradoxically create order by preventing runaway star formation. The mechanics behind this cosmic regulation are astonishingly precise. When a GRB's jet plows into surrounding gas, it creates shock waves that heat the interstellar medium to X-ray emitting temperatures. This thermal energy prevents gas from cooling and collapsing under gravity, the essential first step for star formation. Observations of galaxies like GRB 980425's host show distinct cavities in their gas distribution, with star formation rates dropping by up to 40% near the burst's remnant. These bubbles of hot gas can span thousands of light years, essentially sterilizing entire sectors of a galaxy from new star birth. What's fascinating is how this connects to broader cosmic evolution. Galaxies with frequent GRBs, typically compact, metal-poor systems in the early universe, may experience staggered growth as bursts periodically halt their star-making. This explains why some young galaxies show a bursty star formation histories, with intense periods of activity followed by mysterious lulls. The GRB feedback acts like a thermostat, preventing these galaxies from burning through their gas reserves too quickly, which could otherwise leave them as lifeless husks by cosmic noon. Yet GRBs aren't just destructive forces in this scenario. By preventing excessive star formation, they indirectly extend their host galaxies' evolutionary timelines, allowing them to mature more gradually. The heated gas eventually cools and condenses again, sometimes enriched with heavy elements forged in the burst itself, creating ideal conditions for more stable, long-lived stars like our Sun. This delicate balance between creation and suppression mirrors how forest fires clear space for new growth, maintaining ecosystems on galactic scales. The most dramatic evidence comes from quasar observations. Some distant quasars show absorption lines indicating they're viewing galaxies through GRB-heated gas halos. These spectra reveal telltale signatures of ionized metals spread far beyond the galaxy's visible disk, proof that GRB energy permeates intergalactic space, influencing regions no supernova could reach. It's a reminder that these explosions don't just affect their immediate surroundings, they help shape the cosmic web itself, one feedback loop at a time. This feedback mechanism solves a long-standing puzzle about galaxy diversity. Without some form of star formation regulation, computer simulations consistently produce galaxies that are either too massive or too small compared to real observations. GRBs provide just the right amount of intermittent heating to match the observed distribution, especially in dwarf galaxies where single bursts can have outsized impact. Their role as cosmic moderators might explain why the universe didn't exhaust its star-forming fuel billions of years ago, preserving enough raw material for galaxies like our Milky Way to form at a more leisurely pace. What emerges is a startling cosmic symbiosis. The same explosions that threaten life on nearby planets also ensure galaxies don't burn too bright too fast, maintaining conditions where life could eventually arise. Every GRB is more than a cataclysm, it's a sculptor of galactic ecosystems, carving out the patterns that dictate where and when new stars and potentially new worlds can take shape. In the grand tapestry of cosmic evolution, these brilliant flashes are the needles that keep the fabric from unraveling too soon. The story of gamma-ray bursts begins not with astronomers scanning the cosmos, but with military satellites watching for secret nuclear tests. In 1967, the United States launched the Vela satellite series unassuming spacecraft with a singular mission: to monitor Earth for telltale gamma-ray flashes that might signal unauthorized atomic detonations. These Cold War sentinels orbited in silence until July 2nd, when Vela 4 and Vela 3 picked up something extraordinary. Not a human-made explosion, but a burst of gamma radiation unlike anything in their classified manuals. The pattern was unmistakable, a sudden spike of high-energy photons coming not from Earth but from deep space. At first, the discovery was treated as a military anomaly, filed away under layers of secrecy. The bursts were erratic, appearing at random intervals from all directions across the sky. For 6 years, this cosmic mystery remained confined to classified reports while scientists quietly puzzled over the data. Then in 1973, researchers Ray Klebisadel, Ian Strong, and Roy Olson finally connected the dots. By comparing arrival times across multiple Vela satellites, they proved these flashes originated far beyond our solar system, perhaps even beyond our galaxy. Their groundbreaking paper, published in the Astrophysical Journal, marked the official birth of gamma-ray burst astronomy, though the true nature of these events would remain hotly debated for decades. What made this discovery so revolutionary was its sheer serendipity. The Velas weren't designed for astronomy. Their detectors could barely localize the bursts, let alone determine their distance. Those early observations showed none of the hallmarks we now associate with GRBs: no afterglows, no host galaxies, just fleeting blips on a screen. Yet buried in that sparse data were clues that would eventually rewrite astrophysics. The bursts' isotropic distribution, their equal appearance across all parts of the sky, hinted at either a universal phenomenon or something incredibly close to home. The debate raged until the 1990s, when precise localizations finally proved GRBs were cosmological, occurring billions of light years away. That first detected burst, now catalogued as GRB 670702, was likely a relatively weak event by modern standards. Today's satellites would classify it as a bog-standard long-duration burst, possibly originating from a collapsing massive star. But in 1967, it represented a complete mystery, one that military analysts initially dismissed as a detector malfunction. Had those Vela satellites been slightly less sensitive, or had the data remained classified indefinitely, our understanding of the high-energy universe might have developed very differently. The legacy of this accidental breakthrough lives on in how we study the cosmos. Modern GRB hunters like Swift and Fermi are direct descendants of those early Vela missions, proof that scientific discoveries often come from unexpected places. What began as a tool for geopolitical surveillance became our first window into the universe's most violent explosions, a reminder that sometimes the most profound truths reveal themselves when we're looking for something else entirely. That unassuming burst in 1967 didn't just announce its own existence, it opened our eyes to an entire class of cosmic phenomena we didn't know to search for. And in doing so, it set the stage for 50 years of explosive discoveries that continue to reshape our place in the universe. For decades, astronomers faced a cosmic accounting problem. About half the normal matter in the universe seemed to have gone missing. This wasn't dark matter, but ordinary protons and neutrons, the building blocks of stars and planets collectively called baryons. Telescopes could only account for roughly 50% of the baryons predicted by cosmic microwave background measurements. The rest nowhere to be found. Enter gamma-ray bursts, whose brilliant afterglows act like forensic lights, revealing this hidden matter in the most unexpected places: the vast, near-invisible webs of gas stretching between galaxies. The solution lies in how GRB light interacts with this diffuse material. As the afterglow travels toward Earth, it passes through clouds of warm, hot intergalactic medium, a sparse soup of ionized gas too thin to emit detectable light but thick enough to absorb specific wavelengths. Like sunlight filtering through stained glass, the afterglow's spectrum develops dark absorption lines where atoms in these cosmic filaments have absorbed particular colors of light. Each element leaves a unique fingerprint: oxygen at one wavelength, carbon at another, neon somewhere else. By tallying these absorption features across multiple GRBs at different distances, astronomers have built a three-dimensional map of the universe's hidden scaffolding. What makes GRBs uniquely suited for this cosmic census is their piercing brightness and random distribution. Unlike quasars, another common light source for such studies, GRBs occur in all types of galaxies, offering unbiased sampling of cosmic highways. Their brief, intense flashes also probe regions too diffuse for other methods. A landmark study using GRB 090423's afterglow detected oxygen absorption in gas so tenuous its density was just a few atoms per cubic meter, yet stretched across millions of light years. Multiply such discoveries across hundreds of bursts, and suddenly the missing baryons start appearing, woven into the cosmic web like threads in a spider's silk. The real surprise was where these baryons were hiding. Computer simulations had long predicted that galaxies were connected by filaments of warm gas, but direct proof remained elusive until GRB afterglows exposed their chemical signatures. These aren't the dense molecular clouds where stars form, but rather a plasma so hot it emits mainly X-rays, energies most telescopes struggle to detect at cosmic distances. GRB afterglows bypass this limitation by absorbing those same X-ray energies, effectively using the universe's expansion to redshift the signals into detectable ranges. Perhaps most astonishing is how these discoveries reshape our view of cosmic structure. The missing baryons weren't truly missing. They'd been hiding in plain sight, diluted across enormous volumes where traditional surveys couldn't spot them. Like realizing the air in a room has weight despite being invisible, GRB afterglows have shown us that what looks like empty space is actually a complex network of ionized gas, containing more mass than all stars and galaxies combined. Every time a burst flickers to life, it doesn't just illuminate the darkness between galaxies, it reveals the hidden bones of the cosmos, the unseen framework upon which everything else is built. On Christmas Day 2010, astronomers received an unexpected gift from the cosmos, a gamma-ray burst so strange it earned the nickname the Christmas burst. GRB 101225 wasn't your typical GRB. Instead of the usual rapid spike and smooth decay, its light curve looked like a holiday light display gone haywire, erratic flickers spanning nearly half an hour, followed by an afterglow that refused to follow the standard playbook. This wasn't just another stellar explosion, it was a cosmic puzzle wrapped in festive mystery, challenging everything scientists thought they knew about these powerful events. The burst's bizarre behavior started with its duration, 28 minutes of on-again, off-again gamma-ray emissions far longer than most long GRBs. But the real head-scratcher came days later when optical telescopes spotted something unprecedented, an afterglow that initially faded, then abruptly brightened again as if someone had hit a cosmic dimmer switch. The color changes were equally perplexing, shifting from blue to red over weeks. Normally, GRB afterglows evolve predictably as different wavelengths fade at set rates. This one behaved like a cosmic mood ring, its spectrum twisting in ways no standard model could explain. Debates over its origins ignited almost immediately. The leading theory proposed a scenario straight out of astronomical folklore, a neutron star shredding an asteroid. Picture a dense stellar corpse wandering too close to a rocky body, its immense gravity stretching and tearing the asteroid apart in a process called tidal disruption. As the debris rained down onto the neutron star's surface, it would have ignited sporadic thermonuclear explosions, producing the burst stop-start gamma-ray signature. This explanation would make GRB 101225 the first known example of an interstellar Christmas dinner, with a neutron star devouring celestial leftovers. But the plot thickened when alternative explanations emerged. Some researchers argued the burst's light curve better matched the collision of two neutron stars, a rare event that typically produces short GRBs, yet here lasted suspiciously long. Others pointed to an unusual supernova signature in later observations, suggesting a massive star's collapse with atypical jet formation. The most tantalizing and controversial hypothesis proposed a completely new class of event, a quark nova, where a neutron star's core collapses further into exotic quark matter, triggering secondary explosions weeks after the initial burst. What makes this cosmic Christmas present so valuable is how it exposes the limits of our GRB classification system. The burst refused to fit neatly into either short or long categories, straddling the line like a holiday that blends traditions. Its afterglow's strange rebrightening hinted at complex environmental factors, perhaps the jet plowing through previously ejected stellar material or interacting with dense circumstellar clouds. Every anomaly became a clue, suggesting progenitor systems far more diverse than our textbooks described. Years later, the Christmas burst remains a teaching moment for astronomers. It reminds us that for all our models and categories, the universe still delivers surprises that force us to rethink assumptions. Whether it was a neutron star's snack, a delayed stellar death, or something entirely new, this festive anomaly proved that cosmic explosions don't follow human-made rules, they write their own, often when we least expect it. And like all great holiday mysteries, the truth might still be out there, waiting for future observations to unwrap its secrets fully. Gamma-ray bursts may hold the key to unlocking one of physics' greatest mysteries, the nature of spacetime itself at the smallest scales. When the highest energy photons from these cosmic explosions race across billions of light years, they carry with them subtle clues about the fundamental structure of reality. According to some theories of quantum gravity, spacetime isn't perfectly smooth like we perceive it, but rather foamy and turbulent at unimaginably tiny scales, smaller than a trillionth of an atom's width. This hypothetical quantum foam could cause ultra-high-energy gamma rays to travel at slightly different speeds, with the most energetic photons slowing down just a fraction as they interact with this frothy spacetime structure. The challenge lies in detecting these minute differences. When a gamma-ray burst erupts, it spews out photons across an enormous energy spectrum, from low-energy gamma rays to photons packing trillions of electron volts. According to Einstein's relativity, all these photons should arrive at Earth simultaneously, regardless of energy. But if spacetime possesses this quantum foam texture, the highest energy photons might lag behind by mere milliseconds over their billion-year journey. It's like dropping marbles of different weights through molasses. In ordinary spacetime, they'd fall together, but in quantum foam, the heaviest might drag ever so slightly. This is where gamma-ray bursts become nature's perfect laboratory. Their brief, intense flashes, some lasting just milliseconds, provide the stopwatch needed to measure these potential delays. In 2009, the Fermi Gamma-Ray Space Telescope observed a burst designated GRB 090510 with photons ranging from 8,000 to 31 billion electron volts. The expected quantum gravity delay should have been about 0.0008 seconds, but all photons arrived within 1 millisecond of each other. At first glance, this seemed to rule out certain quantum gravity models, yet the story isn't that simple. Different theories predict varying degrees of energy-dependent delays. Loop quantum gravity, one of the leading approaches to unifying quantum mechanics with general relativity, suggests the effect might be too subtle for current detectors. Some modified theories propose the delays only become apparent at energies beyond what our telescopes can measure, or that the effect depends on the photon's polarization, adding another layer of complexity. What makes GRBs indispensable is their ability to test these predictions at energies and distances impossible to replicate in any Earth-based experiment. The implications of finding such a delay would be revolutionary. It would provide the first experimental evidence that spacetime has a discrete structure at quantum scales, potentially validating theories that have remained purely mathematical for decades. Even null results help physicists refine their models, gradually narrowing down how quantum gravity might operate. Every gamma-ray burst that lights up the sky isn't just an explosion, it's a potential key to reconciling Einstein's smoothly curved spacetime with the jittery quantum world. Future observatories like the Cherenkov Telescope Array, with its unprecedentedly precise timing capabilities, may finally detect these subtle effects if they exist. Until then, each gamma-ray burst serves as a natural particle accelerator stretching across the cosmos, probing the fabric of reality in ways no human-made machine ever could. The universe, it seems, has been running its own quantum gravity experiments since long before we thought to look. We just needed the right cosmic messengers to reveal them. Some of the most puzzling cosmic afterglows appear without their gamma-ray bursts, like finding smoke without fire. These orphan afterglows shine in X-ray, optical, or radio wavelengths, yet their parent explosions remain frustratingly absent from gamma-ray detectors. The explanation lies in the geometry of GRB jets. While most bursts are visible when their ultra-focused beams point directly at Earth, those angled slightly away, what astronomers call off-axis, might miss our detectors entirely. But as these misaligned jets plow into surrounding gas, they create a delayed, wider spray of emission that eventually becomes visible as a fading afterglow. It's the cosmic equivalent of hearing an echo without the original shout. These orphans provide critical clues about the true GRB population. For every burst we detect head-on, statistical models suggest 5 to 10 others fire off unseen into the darkness of space. By counting these afterglow-only events, astronomers can estimate the universe's total GRB rate, like census workers inferring a city's population by studying neighborhoods missed in initial surveys. One of the first confirmed orphans, GRB 100425A, appeared in 2010 as a mysterious X-ray flare with no gamma-ray counterpart. Only when researchers matched its expanding radio emission to models of off-axis jets did the pieces fall into place. The physics behind these stealth bursts reveals just how narrow GRB jets really are. Typical opening angles measure just 1 to 5 degrees. Imagine a flashlight beam so tight it could illuminate only a quarter of the full moon. At greater angles, the relativistic beaming effect that amplifies gamma rays fades rapidly, rendering the burst invisible to our detectors. But the afterglow tells a different story. As the jet decelerates and spreads outward, its emission becomes visible at wider angles, often peaking days or weeks after the initial explosion. This delayed rise creates a distinctive light curve signature, a slow brightening followed by a gradual fade that sets orphans apart from other transient phenomena. What makes these wayward afterglows scientifically invaluable is their ability to test jet structure theories. Some models predict jets have sharp edges like laser beams, while others suggest they feather gradually like torchlight. Orphans provide the three-dimensional view needed to distinguish between these scenarios. By measuring how afterglow brightness changes with viewing angle, astronomers can literally map the jet's energy distribution. A recent study of orphan GRB 160821b, discovered by its radio emission, revealed unexpected energy in the jet's outer layers, hinting that even the mist bursts might contribute more to cosmic metal enrichment than previously thought. The hunt for orphans has become a new frontier in multi-messenger astronomy. Projects like the Zwicky Transient Facility scan the skies nightly for these subtle, slow-evolving transients, while radio arrays like the Very Large Array catch their long-lasting echoes. Each discovery helps calibrate the universe's hidden GRB sensors, suggesting we might be missing up to 90% of these explosions due to orientation effects alone. That means every brilliant burst we witness represents countless others firing unseen into the void, their afterglows the only whispers of their existence. In mapping these ghosts, we're not just counting cosmic explosions, we're learning how to see the universe through eyes that don't depend on perfect alignment. Gamma-ray bursts might be more than just cosmic fireworks. They could hold the answer to one of the greatest questions in cosmology: how will the universe end? As these distant explosions flash across the cosmos, they carry hidden clues about the expansion rate of space itself, offering a rare glimpse into the ultimate fate of everything. The key lies in how GRBs interact with the mysterious force known as dark energy, which currently drives the universe to expand at an accelerating rate. By studying bursts from different cosmic epochs, astronomers can track whether this expansion has changed over billions of years, a critical test for determining whether we're heading toward a slow big freeze, a violent big rip, or something even stranger. What makes GRBs ideal for this cosmic detective work is their sheer visibility across time and space. Unlike supernovae, which fade quickly, or galaxies, which evolve dramatically, gamma-ray bursts provide consistent, high-energy markers that can be compared across the universe's history. When scientists analyze the afterglows of extremely distant bursts like GRB 090423, they're not just measuring distance, they're taking the universe's pulse at different ages. The subtle changes in how these afterglows dim and shift reveal variations in the expansion rate, effectively creating a cosmic speedometer stretching back to the universe's adolescence. The stakes couldn't be higher. If dark energy's strength has remained constant, as the cosmological constant theory suggests, the universe will continue expanding indefinitely, culminating in the Big Freeze, a cold, dark fade into oblivion as galaxies drift apart and stars burn out. But if GRBs show that dark energy is growing stronger over time, it could point toward the more dramatic Big Rip scenario, where even atoms get torn apart in the final moments of existence. Some of the most intriguing data comes from comparing GRB brightness at different redshifts, a technique that hints dark energy might not be constant after all, but rather evolving in ways we don't yet understand. One groundbreaking study used over 100 gamma-ray bursts as cosmic mile markers, mapping the universe's expansion over the past 12 billion years. The results showed unexpected fluctuations in how quickly space was stretching at different epochs, challenging simple models of dark energy. These anomalies suggest our universe's fate might be more complex than either the Big Freeze or Big Rip scenarios, possibly involving unknown physics that only GRBs can help uncover. Future observations with next-generation telescopes could settle the debate by capturing bursts from even earlier times, tracing the expansion history back to the cosmic dawn. What makes this search so profound is that gamma-ray bursts don't just illuminate the past, they shed light on the future. Every distant flash we analyze adds another day to point to our cosmic timeline, helping predict whether the universe will end with a whimper, a tear, or something beyond our current imagination. As we gather more of these explosive breadcrumbs across space and time, we're not just studying the universe's history, we're reading its final chapter before it's written. The hunt for gamma-ray bursts is about to enter a new golden age, thanks to an upcoming generation of telescopes designed to push the limits of cosmic detection. Imagine instruments so sensitive they could spot a birthday candle on the moon. That's the level of precision we're talking about with projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time LSST. This ground-based powerhouse will scan the entire visible sky every few nights with a 3.2 gigapixel camera, catching the faintest afterglows that current surveys miss. Its rapid-fire observations could reveal orphan afterglows from off-axis bursts previously invisible to us, along with ultra-long GRBs that fade too slowly for today's detectors. But the real game-changer, LSST's ability to spot the infrared signatures of bursts from the universe's first billion years, a window into stellar populations we've only theorized about until now. Then there's the James Webb Space Telescope, JWST, already rewriting the rules of infrared astronomy. While not a GRB hunter itself, JWST's unmatched sensitivity to redshifted light makes it the perfect partner for follow-up observations. When Swift or Fermi detects an extremely distant burst, JWST can dissect its afterglow in unprecedented detail, analyzing chemical fingerprints from eras when the universe was a fraction of its current age. Its recent studies of GRB 221009A, the BOT burst, revealed unexpected molecular signatures in its host galaxy, suggesting GRBs might occur in environments richer with complex chemistry than previously thought. Future targets could include bursts from population Roman III stars, the universe's mythical first generation of stars composed purely of hydrogen and helium. The dream of spotting a population Roman III GRB drives much of next-gen telescope design. These hypothetical stars, hundreds of times more massive than the Sun, would have lived fast and died in spectacular hypernova, producing GRBs with unique energy signatures. Facilities like the European Space Agency's Athena X-ray Observatory, launching in the 2030s, could identify these relics by their unusual X-ray afterglows, which would lack certain metal absorption lines since population Roman III stars formed before heavy elements existed. Meanwhile, radio arrays like the Square Kilometre Array SCAR will listen for the faint echoes of these explosions in the cosmic dark ages, tracing how their shockwaves interacted with pristine intergalactic gas. But the future isn't just about bigger telescopes, it's about smarter coordination. Projects like the Gamma-ray Burst Ultraviolet Near-Infrared Optical Telescope GUNAMIT aim to launch swarms of nanosatellites that autonomously reposition to catch GRB afterglows within seconds. Combined with AI-driven alert systems that prioritize bursts based on real-time analysis, we're moving toward a global network where every explosion gets immediate multi-wavelength attention. The goal: to transform GRBs from isolated curiosities into an interconnected data stream, each burst a pixel in humanity's growing image of the high-energy universe. What makes this coming era so thrilling isn't just better technology, it's the potential to answer existential questions. Are we alone? How did the first stars shape the cosmos? What governs the universe's expansion? Gamma-ray bursts, those fleeting cosmic messengers, might hold clues to all of them. With each new telescope we point at the sky, we're not just building better cameras, we're crafting new eyes to see deeper into space and time than ever before. And who knows, the next burst detected could be the one that rewrites the textbooks, revealing corners of reality we've barely begun to imagine. From the faintest whispers of the early universe to earth-shaking blasts that could sterilize entire galaxies, gamma-ray bursts have taken us on an extraordinary journey through space and time. These 30 astonishing facts reveal just how much GRBs teach us not only about stellar explosions, but about the universe's most extreme environments. They've shown us newborn black holes screaming into existence, neutron stars colliding to forge cosmic gold, and even the hidden scaffolding of matter between galaxies. GRBs illuminate the darkest chapters of cosmic history, acting as both time machines and flashlights peering back to the first stars while exposing the invisible structures shaping our universe today. But perhaps the most humbling realization is how much we still don't know. Every record-breaking burst, whether the BOT's blinding fury or the Christmas burst's erratic flickers, challenges our assumptions, proving the cosmos still holds surprises. These explosions aren't just endpoints, they're catalysts seeding galaxies with heavy elements, regulating star formation, and even influencing the potential for life itself. In their terrifying power, we find unexpected connections linking the death throes of distant stars to the gold in your jewelry, the ozone in our atmosphere, and the very fate of the expanding universe. So as we close this cosmic dossier, one question lingers: what will the next gamma-ray burst reveal? A population Roman III star's final cry from the cosmic dawn? A new class of magnetic monster, or something beyond our wildest theories? The universe writes its secrets in bursts of light, and the next chapter could be just a telescope alert away. If you're hungry for more cosmic mysteries, hit subscribe and join us as we keep watching the skies, one explosive discovery at a time. Because in this vast, dynamic cosmos, the greatest show isn't here on Earth, it's out there, where black holes are born, stars collide, and the universe itself keeps rewriting the rules.